Hello everyone, we are the students of Vishwakarma Institute of Technology Pune. Welcome to this video on interrupt driven input output. Have you ever wondered how your computer can handle multiple tasks at once, like downloading a file while you are browsing the web? It's all thanks to interrupt driven input output, a key concept in computer architecture that allows devices to communicate with the CPU without monopolizing its attention. In this video, we will explore how interrupt driven IO works and why it's essential for modern computing. So, we are Group 5 from Division H, and today we'll be sharing our knowledge about interrupt driven IO to you. So, let's get started. Interrupt driven input output is a technique used in computer systems to improve the efficiency of input output operations. It allows the computer system to process data in parallel, which means that it can perform other tasks while waiting for input output operations to complete. Interrupt-driven input-output uses interrupt to signal input-output transfer completion instead of polling. When a device needs to transfer data, it sends a signal to CPU to set a program interrupt, which means the device signals the CPU using hardware interrupt, which the CPU handles through an interrupt service routine. Then, the CPU enters an interrupt service routine to handle the interrupt. Interrupt-driven input-output requires a more complex hardware and software than polling. Then it is widely used in modern computing systems for efficient data transfer. This figure shows simple interrupt processing. In the hardware part, what basically happens is that some drive controller or other system hardware comes as an interrupt. Then processor finishes execution of the current instruction, then it signals acknowledgement of the interrupt. What happens next is that processor pushes PSW and program counter on the control stack, which then loads new program counter value based on the interrupt. This was all about the hardware part. Now, followed by the software part, it saves the remainder of the process state information. Then it processes the interrupt, which is then followed by restoring process state information, and then finally it restores the old PSW, that is program status word, and PC, that is program counter. Now here we will see how device interrupt work for input and output differently. Interrupt driven input output efficiently handles the input and output operation by allowing the input devices to interrupt the CPU when new data is available. And for output devices interrupt the CPU when they are ready to accept the new data. Here the CPU works on its given task continuously. When an input is available, such as when someone types a key on a keyboard, then CPU is interrupted from its work to take care of the input data. The CPU can work continuously on a task without checking the input devices, allowing the device themselves to interrupt it as necessary.
So what are the basic operations of interrupt? So basically there are four major operations of interrupt. CPU issues, read command, input output module gets data from peripheral whilst CPU does other work. Input output module interrupts CPU, CPU requests data and the input module transfers data. What are the major functions of interrupt processing? So, interrupt processing is a fundamental mechanism used by computer systems to handle unexpected events or signals from external sources. These events, known as interrupts, are typically generated by hardware devices such as input-output devices or timers to gain attention from the processor. Here are the key steps involved in the interrupt processing mechanism. Interrupt request. An interrupt request is generated by an external device and sent to the processor. The device assigns a specific interrupt line to indicate the type of interrupt. Interrupt acknowledgement. The processor receives the interrupt signal and identifies the source of the interrupt. Context switch. The processor saves the current execution context including the program counter and register values onto the stack. Interrupt vector table. The processor uses as an interrupt vector table or descriptor table to determine the address of the corresponding interrupt handler for the specific interrupt being processed. Interrupt handler execution. The process jumps to the address specified in the interrupt vector table, which points to the start of the interrupt handler routine. Interrupt servicing. Once the interrupt handler completes the task, it signals the processor that the interrupt has been serviced. Resuming execution. The processor resumes the interrupted program's execution, returning to the point where it was interrupted. Interrupt processing allows the system to efficiently handle events that require immediate attention without relying on the processor to continuously poll for device status. By using interrupts, the system can promptly respond to external events, improve overall system performance, and enabling multitasking capabilities. This is how the interrupt processing occurs. This is the flowchart of the interrupt processing. Issues read commands to the module. Then the read status is uploaded to the input output module. It checks the status of the error condition, and then it reads the word from the input output module, and then the written word is into in the word is written into memory. After that, the next instruction is done.
So advantages of interrupt-driven I/O are it is faster, efficient, and easy to use. And disadvantages are it can be tricky to write if we use a low-level language. It can be tough to get various pieces to work well together. It is usually done by the hardware manufacturer or OS maker. Example, Microsoft. Next, design issues. There are two main design issues for interrupt-driven I/O. How does the processor decide which device issued the interrupt signal? And how does the processor decide which module to process when multiple interrupts have occurred? There are four main ways to counter these problems, which are multiple interrupt lines, software pole, daisy chain, also known as hardware pole and vectored, bus arbitration, also known as vector.
Techniques for identifying the source of interrupt. The simplest solution to identify the source of interrupt that we will be providing each line for communication to each device. So whenever an interrupt comes from any line, we could easily decode from which line the interrupt has come. Whenever an interrupt is detected by the processor, it branches an ISR interrupt service routine which will poll each and every IO module to determine the exact interrupting module. Then the processor will raise a poll which could be in the form of command line. Consequently, the address of respective IO module which is interacted by the poll will be placed to the address line. The module will then respond positively if it is responsible for setting up interrupt. Then we come to hardware pole. This is actually hardware pole, also known as daisy chain pole. The interrupt acknowledge line is daisy chain to all modules. Whenever there is an interrupt, the processor send out an interrupt acknowledge which will propagate throughout the series of IO modules. This process will continue until it reaches a requesting module. The module will respond by placing a word on the data lines. The word is also known as vector. This vector can either be the address module or be the specific identifier for that address. Bus abbreviation. The last method, which also utilizes vector interrupt, is called bus abbreviation. This method involves IO module gaining control over the bus before requesting of the interrupt. This is limited only to module over a time. The processor sends an acknowledge signal whenever it detects an interrupt. The requesting module then places its vector address on the data lines.
Design issues. However, when there are multiple interrupts at a single time, there will be a need to assign priorities. These four methods have their own way of assigning priorities. Multiple interrupt lines. The processor picks the interrupt lines with highest priority. Software poll. The priority is determined by the order in which the modules are polled. Daisy chain. Hardware poll vectored. The priority is determined by the order in which the modules are polled. Bus arbitration vectored employs a priority scheme.
Input register. The INPR input register is a register that includes 8 bit and influences alphanumeric input data. The 1-bit flag FGI is a control flip-flop. When new data is accessible in the input device, the flag is set to 1 bit. It is cleared to 0 when the data is approved by the device. The flag is needed to synchronize the timing rate difference between the input device and the computer. The data transfer procedure. The input flag FGI is set to 0 when the user clicks any key on the keyboard. An 8-bit alphanumeric code is transferred into INPR and the input FGI is set to 1. The device tests the flag bit. If the bit is 1, thus the data from the INPR is transferred to AC and together FGI is cleared to 0. When the flag is cleared, new data can be transferred into INPR by introducing another key. Output register. Working on the output register OUTR is equivalent to that of the input register INPR. Therefore, the control of data flow is in the opposite direction. Data transfer procedure. The output flag FGO is set to 1. The device tests the flag bit. If the bit is 1, the data from AC is shared to UTR and concurrently LGO is cleared to 0. After that, the output device receives the code 8-bit data and prints the matching character. After this operation is done, the output device sets the FGO to 1. That was all in our today's video. So if you found our video to be helpful to you, you can do like, you can share the video and subscribe to our channel and press the bell icon to getting the notifications of the upcoming video from our channel. Thank you.